Now, total internal reflection seems almost an inconsequential thing. Why do we need to know about some phenomena that is only seen in very special circumstances? And well, the reason we need to know about it is because it has so many very useful applications. And you would be staggered to know just in the number of ways in which total internal reflection actually plays a part in our daily lives. You may have seen one of these before. This lamp here basically is what's known as a fibre optic lamp. And the light that is going into the bottom of the lamp is bringing to the top of these fibre optics here. And they're actually used in Christmas trees and all sorts of things. Now in this section we shall try to have a look at how total internal reflection gives rise to the applications of optic fibres, endoscopes and periscopes. Okay, now as before we have a laser that is travelling across here, and what I'm going to do is I'm going to deflect its path using this little mirror here. Now you can see the laser is going up there. Following the law of reflection, if you remember, the angle of incidence is equal to the angle of reflection. And now I'm going to put another mirror parallel to the first, and you can see that I have sent the ray of light to the side and then carried it on forwards as well. Now of course I wouldn't have to do that just there, I could do it right up here. It means that light coming in goes through this spectacular dog's leg. What I have here is of course a periscope. So you might have seen in films and things that people in submarines especially, but not just in submarines, people in trenches as well, if they want to see but they don't want to stick their head up, then what they can do is they can put up a periscope. It's basically a long tube, and this enables them to look through one end, and what it's done is it's sent the light into the tube, down the tube, and then back towards the person that is observing once more. Now, periscopes are very, very useful, but they don't actually normally involve the use of mirrors. They normally involve the use of prisms instead. So what I have here is I have a prism. Now just to be clear, what a prism is, it has a triangular cross-section and then three flat sides around the edge and then another triangle on the other side. Now what happens to a prism if I send the light in? Then what I will find is that the light strikes the rear surface of the prism at a greater angle of incidence than the critical angle. Now that means it is totally internally reflected instead of transmitted through. And so what I can therefore do is I can create exactly the same effect as before, the effect of the periscope, using two prisms. And now this is brilliant because these prisms can be aligned very, very carefully, and the surface that does the reflecting is inside the glass, so it stays very clean. And what you actually find is this technique of using prisms is often used in things like binoculars to shorten the optical path. A telescope is a really long thing, but if you have the light basically bouncing backwards and forwards upon itself, you can get it to do its focusing in a much shorter distance. And prisms, using the principle or the phenomenon of total internal reflection, they use this as well. Now this is where it gets very interesting indeed. You see, what I've got here is a curved piece of perspex, and I'm going to shine a laser light into it. And you can see that if I shine a laser into it, that what happens is the laser light is totally internally reflected off the inside surfaces of this curved piece of perspex. Doesn't matter how I move it, the laser light always goes through the perspex and comes out the other side. The laser light cannot get out the sides. There's no laser light on my hands at all. And so the laser light is capable of following a curved optic fibre because it is reflecting at an angle greater than the critical angle off the inside surface of the material. And then this is the explanation for the optical fibre lamp, is that what is happening is a light is shining in here and it is reflecting on the insides of each individual optic fibre, and even if I bend it, it is still being able to come out the other end again, because it doesn't matter what I do to the direction of this, it always comes out the other end. The angle of incidence is always greater than the critical angle. Now this is more than just pretty. This is actually really, really useful. What they use this for is communications. By shining very, very bright lasers down optical fibres, they can have information transmit around the world at the speed of light. And with lots of different cables, you can also have lots of different communications going on. Each one of these fibres could represent an individual computer connecting to the World Wide Web. The principle of total internal reflection is one of the driving parts of physics for the creation of the internet. And so this is monumentally important to the modern world, because without it we would not be able to communicate in the way that we do. Before this technology, we relied on running a very, very, very long electrical circuit across the world. Now, a very fine optic fibre can transmit the message almost instantaneously from one place to another. So one final piece of equipment that I want to show you that uses this technology is the endoscope. Now, generally speaking, the endoscope is used for examination of the digestive system. It can either be passed down the throat or through the anus, and it's more subtle than you might imagine. There is an optic fibre in here, but not just one. What happens, this is the control where a certain amount of manipulation can make the actual thing move and look wherever they want. But here is where the light actually enters in. But if I shine a laser through here, you can see like a little pair of headlights. What is going on here is my optic fibre can look around and do whatever it wants and illuminate the scene inside your body. The light then reflects off the inside of your body and passes back up the endoscope. If I imagine that the reflected light, what you can now see is the light is now passing back up through the endoscope to the camera that would be attached on this side. Now it's a subtle thing, and I want to take you through it step by step. So here I have the endoscope. This part of it would be connected to a strong and bright light source that basically would be able to shine light inside the patient. So I'm going to pop that in my pocket and imagine that I am the light source. The doctor would then proceed to pass this maybe up the nose and then down the throat. That's a common way to do it. In the mouth, but there is a gagging reflex that makes that quite unpleasant, or through the digestive system, through the anus. And what the doctor would then do is send it all the way down, and using the controls, be able to manipulate the end of the endoscope to look at exactly what the doctor wants to have a look at. And they could pass it through the stomach, through the duodenum, into the intestine to investigate pretty much anywhere they want to go with this technology. Endoscopes are also used in other situations as well. They can be used in, for example, in disaster recovery. If there's people buried in some collapsed building, for example, they might be able to send an endoscope down to have a look, and it would be able to do so. There are other uses as well of endoscopes, but these are the main ones. So, how does it work in a nutshell? Well, try to put it on the table without it slinking away. You have an observer here. Now, I've drawn an observer who's looking through like a little eyepiece lens. Generally, you don't get endoscopes anymore that you physically have to put your eye to. Normally they come up to a screen and the doctor can look at the screen to see what's going on. And this is connected to the controls of the endoscope. And then there's the endoscope cable that goes into the patient like this. But what is interesting is, and I'm going to draw it slightly differently, as if it's two cables that go in. One of them has the light source going in. And you've got to imagine that this is down a person's throat. There is their mouth, there is their nose, there is their eye, and this is going inside their body to the cavity of their stomach. What happens, of course, is, and I've got to try to draw this a little bit better here. Let's try and draw it more accurately. Is, I'm going to use a different colour, the light source, the light goes in and total internal reflection occurs, which causes the light source or the light to pass all the way down this cable inside the person's body, where it shines out and reflects all around, illuminating the inside of the stomach. So it's totally dark inside your body. If you put a camera in there, it would just see black. You have to send lights in as well. Now some of that reflected light actually ends up going back into the other optical fibre and moving back out of the body once more. Where it can then be observed by the doctor. So optic fibres, endoscopes, and the technologies that they enable, such as the diagnosis of problems in the digestive system, the internet, and fibre optic Christmas trees, periscopes, they are all because of total internal reflection. That is why you need to know about it.